Okay. Hello, everyone. So, anyone joining the yesterday makeup exam? I hope you get good results. I haven't checked your score yet. Maybe next week I will finish. Okay. So, since we are in early December, and yeah, I think the government, they just posted new rules starting from 1st December about the mask. You can check that out. So the chapter 6. I hope everyone watched the video yesterday that I posted about the area, volume. Okay? So it's actually all the contents for this chapter 6 mostly. Okay? I would like to just add one more section for today, and maybe some introduction for chapter 7, and some review for several questions. And maybe within this week, I will give you exercise for chapter 6. Okay? Supposedly yesterday, but I haven't finished the questions yet for the exercise. So let me start with some review. Okay, some review. So let me start from the area. Okay. So the area. Let's say we start from here. Okay. So area, or maybe not this one, maybe here. So area, the idea or the most critical aspect for finding the area between the curves is to determine the rectangles, the sample rectangles. Okay? That rectangle will determine will we using the dx or dy. Okay? So for example, this part here, we could take the dy like this. Okay? Because if we take dx, let me just get you some illustration. If you take dx, you will have a problem here. Okay, see the orange one? If we take the rectangle and we take the integration with dx, it's supposed to be top minus the bottom, but it's the same curve. Okay, so that's the problem. So we couldn't do this part. Okay? So it's better to get this blue and red, which is the left and right, which we are going to take the dy. Okay, I hope you get that illustration. And that's how we find or identify the problem. Okay, so we are going to have dy. But there is also another problem that we can take both. Okay, like this case. Every time we have some intersections here, it means that at some point the equation will be changed. If we take, for example, the dx like this, it's dx. Well, we see from this part maybe, okay, and we move our rectangle, and up until here, they will slightly change the curve on the top, right? That's why we are going to separate the area. So it can be becoming area 1 and area 2. Okay. So the first area, the area 1, this is the curve on the top. This is on the bottom. Okay. For area 2, now it changes to the red curve on the top, and still the same on the bottom. So A1 plus A2. And then its integration, the endpoint of the integration will also be changing. Okay? So we could start with from 0 to 1 for A1 and 1 to 2 for A2. Okay? But I think we could also try to take this green dots here and make it A1 and A2 and take dy. It's also possible. Okay? It's also possible. Okay, so the key is finding the first is there any intersections, and then deciding which integration you are going to go through, dx or dy. Okay,
This is for dy. Okay. You could have a1, a2 like that. Okay. The same results, supposed to have the same results. Okay. And then let me go through the volume. The volume, as you see the video, we could get the formulations through, or maybe here. So the idea of the volume is
it will be based on the area. So how you identify the area from the previous sections will be also determine the same area here.
okay. So the key is, let me just go here. The key is if we have some curve,
and of course, if you imagine like the area between curves, like in the previous one, and imagine that area will be rotating within the y-axis, x-axis, or other line as well. You can also rotate that. So for example, if we take this, we will have this solid, right? It's solid. And the key is, imagine that there is like a small section, like just a sample. If we slice this, it's like a disc, right? Like a disc. And the idea is the area of that disc, which is the circle, we multiply with the thickness, which in our case here is the dx, the height. It's like just like a cylinder, the disc, right? We could also tell this method is also named as the disc method, maybe in the other textbook as well. Okay.
and the key is still the same with previous sections. So we may need to draw to give illustrations which rectangle we want to take sample. Is it the dx or dy? And for example, this one we take for dy because we rotate through the y-axis, this part, okay? And then we might also have this, okay?
It's actually, we could have like multiple questions. Like it's maybe the first one asking the area, and then we can rotate here, we can rotate here, or we can rotate into another line. Okay? We can have a multiple question. Right?
So I think the very first thing, if there is no image available, then you need to illustrate how the graphs look like. Okay. Okay. And then there's another example that you can check the video. Okay, I think this is the same. And another method is if we have this. Okay.
If we have this, and we want to rotate here. So every time you see this type of graph, you will see that, again, it's the same confusion, which part is your top and bottom, or left or right, because it's the same curve. So that's why we need another approach for the volume. How we approach this, we are going to have this cylindrical shell. So we are going to make the samples, the rectangle here, and then we rotate, and supposedly it's like a cylinder but hollow. Okay? So we take this approach, as I think I already giving you some explanation and description on what is this. So we are going to take, there's three components: the circumference of the circle, that's the cylinder, the circumference, the height, and the thickness, the delta R.
So if we take this, we are going to have this kind of structure. Let me just get you to the example here. Okay.
I think the easy way to visualize why does the volumes, the formulations like this, it looks like this. You could take this and slice and cut open. It will be a rectangle, okay, rectangular shape, which we can take this for the length, width, and the height, right? And then for our example, we could take the same curve here. This is our, this function will be our height. This is our R. So our r in our case here, we are going to take as just variable x. So we take x, so 2 pi r is x, and then the height, and then the dx is the delta r. So the delta r is 1. If this is r, then the delta r here. So this is the dx. And basically just multiply, integral, and that solves everything. Actually, this cylindrical shell will work for all types of questions in polygon. But sometimes maybe it takes too long. So you can have options. We'll choose the normal one, the disk one, or the cylindrical shell. Sometimes you can have two options. But sometimes if you can identify through the graph, you will notice that for any graph that looks like this, then you can definitely just go to this shell method, for the cylindrical shell.
Okay, I think we could have some okay, maybe first is this, find the area. Let's just take review for some samples, and I will give you one more section on the chapter 6. There is actually one section about work, like in physics, but I think I will skip that. Okay, I will skip that.
So the graph is already been given, so you can just take a look at the question, the equation, the area. I think intersection are also given, so you could directly put into your integrations formulation. I think you could choose the y or the x, right? And then taking some cut into pieces. We just two pieces. Okay, anyone? Get the yeah, I think just like seeing some computation. Yes. Yeah, but long. Yeah. Easy but long. Long to run.
Yeah, maybe we get it right. So I think it's just we just taking the I think I will just take this part So taking A1 and A2 like that. So area is A1 plus A2. And A1 is, I will take the dx, right? So let's just say dx here. So we will take integrations from -2 to 1. And then the top equation is the 2 over 3 x plus 16 over 3 minus, what is this? Minus x squared. That's A1. And plus the A2. A2 is from 1 to 2. So integrations 1 to 2. And write the subtractions between -2x plus 8 minus x squared. Okay. And then the x. Yeah, I think this is just be careful on the computation. I think this is quite easy. And plus -x squared plus 8x minus 1 over 3x cubed from 1 to 2. It's supposed to be, the final result is 44 over 3. Okay. Okay. Okay, let me give you another one. So example, okay. Okay, let's try the volume one. Okay. I think just do 10 here. Okay. I think this should be okay. Okay, I have several questions, but maybe not all will be discussed. Maybe take only 2. Okay, maybe number 8 and number 10. But I think maybe number 8 first. Okay, number 8 first. So we have x equal 1 plus y squared and line y equal x minus 3. and then rotate about the y-axis. Okay. So since this type of question is a typical direct question, asking for volume or even the area between curves, you need to be, I think, familiar with the type of these questions. So whenever you have like, you have a curve, so it means the curve is probably the boundary for the region. And the last part here is the center of the rotation. So the region will be rotated through x-axis, y-axis, and then other example as well. Okay. So as long as you can illustrate how the curves looks like, how the region looks like, and how they are rotating, and how the supposed to be solid of revolution looks like, I think that will be the key to determine which curves that need to be subtracted to another one. And the result is just getting by the integral of our formulations. Okay? So after the identifications, after our formulations, I believe that will be the key. Okay, so first, we could try to draw this number 8. So 1 plus y squared. So it's y squared but shifted to the right. Right? I'll shift it to the to the right. Okay. Yeah. So for number 8, so we'll have that 1 plus y squared okay, this is x equal 1 plus y squared, okay, and then y equal x minus 3. Y equal x minus 3, x, this is, let's say this is 1, 2, 3. Let's say 3 is here. So it's supposed to be intersected at that point. And then 1, too small. 1, 2, maybe 3 is there, and then the line okay. So this line is the y equal x minus 3 or x equal y plus 3. Okay, now we have two intersections, this and this. So to confirm our intersection, we could take the 1 plus y squared equaling to y plus 3. So y squared minus y minus 2, yeah. And this will be y minus 2, y plus 1. So y equal 2, y equal negative 1. So this is going to be y equal 2 is going to be here. So when y equal 2, x is equal, let me write here, equal 5. So when y is negative 1, x is 2. So this is going to be 2 and negative 1. This is 5 and 2. Okay. And it's rotated about the y-axis. So rotate going to be here. Okay, rotated going to be there. I think it's clear that we need to take
if we want to take the disk method, we need to take this dy, so we can have the disk method. Right? So we take dy. If we take dx, we have a problem in here. It's the same curve, and we don't know the top and bottom equation clearly.
So we take dy. So let me draw the rectangle here to give you an illustration. So we take dy, and we could see that this will be the how it looks like. Okay. So you could think this like a disk like this. Okay.
This looks like this, right? Now we could take the radius, the volume will be given by the difference in the area. So the outer radius minus the inner one.
We could take that. Let me write. So the right equation, or the outer one, will be the y plus 3, this one, right? So we have to this and this. Let me write here. So volume is pi. I will write pi outside the integrations. Dy is from -1 to 2. Okay, and then the outer radius is y plus 3, and then squared, minus 1 plus y squared, and then squared, and then dy. Okay. The squared is coming from the area, is pi r squared, right? So what we do is taking this is r outer minus r inner. Okay. And then taking the volume, meaning we are multiplying with the thickness, the dy. So we solve this. So this will be y squared plus 6y is 9. Okay. So let's simplify. Plus 6y minus y squared plus y with power of 4. Okay, and then take the integrations. So we pi 8y plus 3y squared minus 1 over 3y cubed plus 1 over 5y with power of 5. And then take from -1 to 2. So a little bit calculation here. Pi 16 plus 12 minus 8 over 3 plus 32 over 5. Yeah, not really good number. And then minus 1, so minus 8 plus 3 plus 1 over 3 and minus 1/5. Oh, oh, sorry. I think it's supposed to be minus. Okay. I think this will be 28, 36, 30, 33 minus 9/3 minus okay, I will just stop there. Okay. I'm lazy. Well, you could count until the end because I have no space. Okay. Well, if you are in the exam, you like answering like this, and still get full points. I believe like sometimes calculation like that is not really proving any points, so it's just the same. Okay. Okay, maybe try number 10. Try number 10. And then I will move to the next sections. Or perhaps maybe we'll have a break after this number 10. Maybe any questions first? Any questions? Any questions? Any questions from this one? Okay, if you really not really clear, let me know, and I will zoom some parts. If you finish this one, try number 10. Try number 10, you have x squared plus 1, and then y equal 9 minus x squared. And it's rotate about y equal negative 1. Okay. First, you need to try and understand the question. Meaning, you need to get to know the area between the curve of this two curves, the region between two curves, and try to imagine how it looks like when you rotate, and then you can decide which method you want to use, and then which dx or dy you're going to use. Yeah, number 10. The first graph like that. And the second graph is supposed to be, maybe no need to draw really correct, just rough. Okay. Up to you.
precise, I think, as long as it's you can know the curve. This one? Oh, okay.
Yeah, I didn't finish the calculation. You can finish.
It's supposed to be 150 minus 33, 117 over 5.
Let me just write here. Answer is this.
Okay, let me give you time for number 10. Okay, number 10.
Oh yeah, it makes no sense.
Yeah. And then rotate about y equal negative 1. And we'll solve it.
Okay, so let me make a new page for the. So first is the curve having the y equal x squared plus 1, and then y equal 9 minus x squared, right? And then y equal negative 1. This is the center of rotation. So this will be let's say this is x squared plus 1, and 9 minus x squared is maybe around maybe here, and maybe like that. Okay, so first thing is finding the intersections. That is going to be for the two curves. So y x squared plus 1 and 9 minus x squared. So 2x squared is 8. So x squared is 4. So x is plus minus 2. So this will be 2. This will be negative 2. Okay. And then 2, 5. And negative 2, 5, like that. And then the line y equal 1 will be here, the center of rotation. Okay, so this will be y equal -1. And the question is, the volume is rotating about this line, right? So I think this is quite direct, and we can just using the normal method, this method. So we could take this, let's say this is this. And rotate, going to be there. Okay, so that's our graphs, and we are going to take the dx. Okay, we are going to take the dx. But of course, the radius
will be a little bit slightly changed because of this line. So you could see that the inner one will be here, and the outer one is up to there. So you need to have like additional distance. Okay, additional distance.
So the radius, if you write directly the volume, let me write here the volume will be pi, or if you write, well, you could just say the area is pi r outer squared minus r inner squared. Okay, and then the volume is A, and then the AX and DX, like that. Okay, and we could directly write pi -2 to 2, and then the outer one is 9 minus x squared, right?
But we have some additional distance here. So if it is just in this y equals 0, we could just minus x, 9 minus x squared. But since we are having the distance, we need to add that distance. Okay.
So 9 minus x squared minus 1, okay, squared. If you confuse on this minus,
You could just see if this is the outer radius from the original one. You need to just need to plus 1 here. The distance is 1, right? From 0 to 1.
and then minus the inner radius is x squared plus 1 minus 1, and then squared. Okay, so this will be pi, so 10 minus x squared. Oh, I forgot the dx. So dx. And then this will be x squared plus 2 squared. Then dx. So volume is still integrations. We haven't integral yet. So this will be 100. Maybe I'll write here. 100 minus 2x squared plus x4. Also, okay. So we are going to have 96 minus 24 x squared, and then the x. And now we can integrate. And since it's symmetry, so I will just take this 0, 2, and then multiply by 2. Or let me write here. We could write this is because of this symmetry. Okay, and then we could take this 2 pi we could just take what is this? Oh yeah, 128 by 2 is 256 pi. Okay, we'll have a break. We'll have a break and we'll continue into the next section. Have any problem identifying the area, volume? Still has? Yeah, I think I will prepare that. Okay, if not tonight, maybe tomorrow, okay? So for your weekends, you can just have a practice for a while. Okay, so the next sections will be the average value and the mean value theorem for integral. So this will be the average value. So by average, okay, I think for some basic statistics, I think you already have that one, I think since elementary school, right? So if we take the y equal f of x, if we want to make the average value, so let's say the y average, I'm going to write y avg for average. This will be, we can say y1 plus y2, and then depends how many y you have. Let's say we have some into some n, okay, n can be any number, and divide by the n itself, right? Okay. This will be the definitions of the average value. Okay. Now, because we define y as a function of x, so we could also define the y average as each of y we will define as function of x. Let's say x1, and let's imagine that it's a sample point. Okay. Until some xn. And then divide by n. And now, remember that in the Riemann sum, if we take the Riemann sum, the approach of Riemann sum, if we have this random functions and we are going to take the volume, or not the volume, the area under the curve from A to B, and let's say we are having this small rectangle here and we define this with the delta x, right? Remember in Riemann sum, the delta x is defined by b minus a divided by n. Okay. Now if we switch the n with delta x, we could write this also, right? Now we switch this n to that n. Okay. So we are going to have y average is equal 1 over b minus a. Since it's b minus a over delta x will be going to the upside, and this will be f. And multiply with delta x, okay? And we could write this in the sum formulations. So we could write 1 over b minus a and the sum, and we could just write f x I, and then we take the sample point as in the Riemann sum we have before, and then through our definition in integral we could take this y average as 1 over b minus a, and then the sum will be the integral. So integral from a to b of f of x dx. Okay, and that's it. That's the average value. So if the question is asking the average value, and you know the a and b, then you could just using this formula. Okay. Okay, and then the follow-up from this average value is it's related to the mean value theorem in integral. Okay. Okay, if you finish this part, I will move to the next one. Now let me move to the next one. So the mean value theorem. So the mean value theorem, if you see the curves, we have y equal f of x. And then if we see from A to B, okay, and let's say we have the FC that is equal to f average, which means when x equals c, the f becomes the f average. Okay. So we could write if function f or y equal f of x is continuous on AB, then exists number c in that interval where f of c is equal to f average is equal 1 over b minus a integrations a to b f of x dx. Or we could write this as equal f of c b minus a. Okay. So if you see the picture, the figure, it's saying that for any positive functions, there will be some number in between AB, which is C, that the rectangle with base AB and the height is f of C will have the same area as the region under the graph of f from A to B. Okay.
So it's saying that this rectangle is the same area with the area under the curve of this y graph.
Okay, so this is the last part on this chapter 6. Okay. So we finished chapter 5, chapter 6. Perhaps I will give you more exercise on 5 and 6. And maybe next week will be quiz for chapter 5. We'll have several days to complete that. Okay. But maybe next week, the weekends time. Okay. Not really necessarily the weekdays. Yeah, for quiz on the chapter 5. Chapter 6 will be maybe another week. Yeah, perhaps just 2 more quizzes and final exam. Yeah.
So the final would be before the year ends?
Hopefully. Hopefully. So after that, then you'll be free. Right? Yeah. Okay, then chapter 6 finish. I want to, yeah.
Just because you're talking about Christmas holidays, the final exam is still going to be on the 26th of December?
Perhaps. Yeah. For now, by default, still on that time. Yeah. Yeah, 5 to the last part. What we will have, either 7 or 8. Okay. If we are not sure about the 8, maybe just 7. Okay, depends on our progress.
If we're not sure about 8, are we going to have like extra lessons in the 2 weeks after?
Perhaps I'm just giving you just additional video just to watch. Yeah. Okay. Okay. Moving on to chapter 7. Chapter 7. This is all about the techniques of integral. So this will be a little bit heavy subject. Okay. Okay, we start with the integration by parts. Okay, as some of you I think already have learned before, but let me just give you some key points of what it is. Okay. Just an introduction. Okay, so first, if we remember at the derivatives, let's say we have these definitions, okay, and then we are going to derive these equations. So we say that this df dx will be product rule, right? So f or df, or maybe let me just write f prime g plus g prime f, right? Okay. Now, if we take the d dx f of g, okay, this is this part, right? This part here. Okay. This is the same as let me write this is f prime g plus g prime f, right? Okay. And let me write the f prime with terms d dx. So this will be the same. So I would like to write down with the d dx only for f and then g and then plus d dx of g and then f, right? Okay, this is a normal product rule. But what we are going to do now is we are taking the integral with respect to x. Okay, with respect to x. So in the fundamental theorem of calculus, we know that if we did this, then the d dx will be removed. Okay? That way, we are going to have f of g, okay? Not f of g, fg, sorry. And then d dx f becomes df. So this will be integrations g df, okay, plus integrations f dg. Or if you want to write the dx, still okay. If you want to write and make sure it's okay, it's the same. Okay, and then we are going to rewrite and move out. So rearrange these formulations, become integration f dg equal fg minus integral g df. Okay. Now if we let's say u is function of x and v is g of x, then du is, with the chain rule of course, this will be f prime x dx, and dv is g prime x dx. Okay, now we could write this as integration f of x, dg is g prime x dx, right? Fg is f of x, g of x, okay, minus g of x, and then f prime x dx. Okay, and then let's change all to the u and v as we define here. So this way we are going to have integrations of u dv equal uv minus integrations v du. Okay. Okay. So whenever you find yourself in a maybe not sure, is it v du or u dv? You could maybe start from the product rule and take the reverse process and take the integral. Okay. Okay. So I'm not necessarily giving you like, okay, you need to use this formula, blah, 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 but the one that you already have learned before, the product rule, and take the reverse process, take the integral. And it will be like this. And this u dt is usually just taking f and g, f and g in the product rule, our product rule at the beginning. So what does it mean? And what does this formulations mean? So every time you have a integral component, okay, like some function inside here, the first thing we need to do in integration by parts is identify whether it is this u or dv. And then we need to set up some components in this right-hand equation. So u, and then dv, we need to get this component of dv to be integrated. Okay? dv integrated becomes v, and then u we derive become du, okay, and v du. Okay. I think I would just give you some example to use it. Okay, how to use it. The simple integrations. For example, we take the ln x dx. What is the integration of ln x dx?
1 over x.
That's derivative.
Yeah.
Okay, this is how the integration by parts will take. Okay? So we know that derivative of ln x is becoming 1 over x, derivative 1, right? So we know that perhaps if we take ln x as u and dx is dv, then perhaps we can rearrange this, right? So first, we are going to have this as u. This is dv, okay. Okay. And then writing. So u is ln x, so du is 1 over x, and then dv is dx. So v is perhaps it's x, okay. And then we take this integrations. So u is ln x. V is x, so x ln x, right? Minus v is x, and du is dx, so x dx. So we start to compute this. X is just v. Oh, v is what? V is x. 1 over x. Sorry. So v is x and 1 over x. Yeah, 1 over x dx. So this will be 1. Okay, 1 integrate becomes just x, so negative x plus constant. Okay, the easiest example thing to come up with. So most of the time, the integration by parts will work. Most of the time, for most cases.
So my suggestions, if you see any integrations, you can think the simple one is the substitution. If you maybe not able to substitute, you can go through this integration by parts. Or maybe some other technique as well, as we follow through the chapter 7. But the two methods that will be really like oftenly used is substitution and integration by parts. The other one may be more efficient, but maybe not for all cases.
Okay, let me give you another view. Okay. Let's say x sine x dx. Okay. Sometimes if you are maybe not able to be identify the UNDV, maybe not really correct, maybe the equation will not be solved, like you will like having some circling integration and the integration will still there. Sometimes we do that. Yeah, I also have experience with that. And then it's circling back to the question, and then it's not solved. Okay. I will give you, if we have time, the tips to get through this method. Really efficient, really quick. Okay, so for this one, we're going to take u is x. Okay, so du will be dx, and dv will be sine x dx. So v is negative cosine x. Okay, this way, we are going to have negative x cosine x, and then it's supposed to be minus cosine x v du is dx. Okay. So this will be plus sine x plus. Okay. Okay, my tips. Okay, my tips.
Okay, you see x sine x. We could imagine this components can be x dx sine x or x and sine x dx, right? Okay. Now if we focus this x and sine x, if we think derivative, if we think x to be derived, at the end of the day, it will reach 0, right? It will reach 0. Okay? For sine x, either derivative or integrations, we're just having sine x to be cosine, sine, cosine, sine, cosine, sine. Never ending. So no problem for sine x. But for x, if we derive at least 1 time, 2 times, it will be 0. So my suggestion is let that x be derived. Okay? to get this integration to be solved. Okay. Now, I will give you my tips, okay? How to make this integration by parts getting more efficient. So we take u, let me write here. Let me write here. So we take integral u d phi, u phi minus phi du. So by this method, we take the u d phi, okay. We integrate. We derive this. We derive this. We integrate this, right? So u derive becomes du. D phi integrate become v. Okay, and according to our signs, this is positive. This is negative, right? So this is positive. This is negative. So we can write in the patterns in the table, okay, to help you to get through. So we write this pattern, and then what we are going to do, let me just write with a different color. So we are going to multiply uv, and then multiply with the positive, and then minus from this one minus this multiplications. Okay. Now the same thing with the integration x sine x dx. Okay, so we take the x and sine x. This is derivative, this is integrations. Okay, so we derive x become 1, derive again becomes 0. Okay. Sine x derive is cosine x, derive again is negative sine x. And now we have plus, minus, plus. Okay. So we multiply here, and 0 is just 0. We don't multiply that one just because of the 0. So this will be x cos x minus plus sine x plus c. Okay. This it's supposed to be multiplied with this, okay, but it's 0. Okay. Very fast, right?
Okay, let me get through again. Okay.
So what this is about is, when you have derivative, you can derive all, and if you know that it will be 0, then let's just derive until 0, and then we can have this shape. But sometimes, both of the components, maybe they are not 0, so you could just stop somewhere. Okay? For example, if we stop until this one, maybe if we take
the x and sine x, and we stop just until here. What we need to write is actually x cos x minus, it's still integral. Okay.
It's still integral. You could stop here and then write like this. Okay? So when we multiply this horizontal line here, it's still in the integral form. This is actually the same thing as we did in the integration by part, but this is just we are making this multiplications to make the
formulations,
these formulations easier to compute. Okay? So it's actually, what we did is, if we take this diagonal line, it means that this part is integration by parts again. It's by parts. So it does like this. Okay? So this is not in your textbook, so I hope you get this one correct. The official one is this, and the official one is this. But this is just how you write this integration by parts in a more efficient pattern, effective pattern. In my course, you can do this, but not sure in other professor. Okay. We are going to review again Next week, don't worry. Okay. This is an introduction. Okay. Yeah, I'd love to give you this part because this is really helpful. It's helped you to avoid some mistakes in your formula here. Because if you, let's just imagine, if you have this, you have another integration, right? You need to solve this. And sometimes you have another integration by parts. And you get that, and maybe another by parts. And then maybe after 3 or 4 times, you get the final result. With this one, you could rearrange the integration by parts, really effective, and really smart. I'm not sure who invented this. I'm not sure. Maybe professor in United States or maybe in Singapore. I'm not sure. But I just got this from my colleagues. Okay, any questions? Any questions? We are going to review again next Wednesday how to get through for most of the cases within this method. Sometimes we cannot get 0 here, so maybe we are going to stop anywhere. Okay, some cases like that, and after that we can solve with other method as well. It's okay.
Well, the answer is positive.
Minus.
Oh, this is supposed to be minus. Right.
Yeah, I forgot to write the integrations.
Yeah, this is supposed to be minus this, and this is minus. Okay. Okay.
Any questions? Yeah. Any questions? If not, I will have a feedback, but the feedback is about the chapter 5. So I hope you can have some review of that. And maybe we could also review next week for chapter 5, just to refresh
Our course. Okay, let's start the feedback. Take this.
But this is about the chapter 5. Okay? So I think I will just review also next week this part, just to give you to refresh the course. Okay?
Okay, I think we can start. Okay, I think we can start. Okay, have you scanned? Okay. Okay. Okay, write your student ID. Okay. So let's start. 3, 2, 1. Okay.
Yeah, I will review this next week. Okay. Using the fundamental theory of calculus. Okay.
That's easy. That's like a derivative.
Yes, it's a combination chapter 4 and 5. So remember the largest is a maximum value. How to get the maximum? Yeah. The graphic is the small f. The question is capital F. Oh. So first is apply derivative, right? To get the maximum value. And then look at the graph. The graph means the capital F prime. Yeah, but the graph is small f. Yes, good. Yeah, good.
Okay. Okay. Get ready for the next one. Okay, get ready. 3, 2, 1. Okay, if this is too small.
F1 is 12, F prime continues. Linear integration from 1 to 4, F prime x is equal to 70. What is the value of F4?
No, this one is easy.
Yeah.
Why am I stuck here?
Like this.
Yeah, I'm just stuck here.
Where?
I don't know. I already refreshed my page. I'm just stuck here. I can't do it.
Oh, can you do it again using the
Okay.
Okay, it's supposed to be really quick. No. It's really simple. Oh, yeah. I thought he said 13 and a half. Yeah. Oh, yeah.
哦，是呀，是，我这次要变第一名了，高职来的。
Okay. Okay, no, not problem, right? No problem. Okay.
第三名而已。
Okay, last one. Question 3. Get ready. Okay.
It's actually the same thing as the chapter 4, the derivative, but it's having the integration in the equations. So you need to apply the fundamental theorem of calculus when you derive the function. Remember, the graph is the small f, it's small f, but the function is the capital F. Remember, concavity is the second derivative, right? The second derivative. But remember, our focus, the function is capital F, and this is our primary function. But the picture is small f. How to find concave downward? We need to find the slope that is decreased.
Yeah. Okay.
我三题选对，我应该是刚对吧？谢谢你。操，第三而已哦。
Yeah. 42, Peter, right? Okay. Okay, good job. Good job. And okay, for the attendance, please write your ID and any feedbacks you have.